Hi, thanks for joining me today for this presentation on the topics of fuel stability and the Dee-Zol Life Fuel Stabilizer from Bell Performance. My name is Ebjornstadabel, and I'm the Technical Information Director here at Bell. And so what we want to talk about today, what we want to cover is we want to cover the issues related to the topic of fuel stability and the chemical treatments that you can use to solve those problems. We want to talk about just cover an overview of the issue of fuel stability. You know, what are the causes of the instability of fuel? How does fuel composition relate to and contribute to those problems? We want to talk about the mechanisms of instability in petroleum. What happens? What are the processes that happen in fuel to make it go unstable? We want to talk about the factors that affect it. What are the things that make it happen faster? What are the things that make it more likely that fuel is going to become unstable? And we also want to talk about how fuels of today compare to the fuels of the past. So in addition to that, we want to talk about the problems that people are going to see in the field when they come across a problem of fuel instability. You know, basically, what does it look like in practice where they're at, where you're at. We want to talk about how to diagnose fuel stability problems, what to look for. And then we want to talk about the treatments, the solutions to help prevent the problem of fuel instability, specifically Dee-Zol Life Fuel Stabilizer from Bell Performance. And then lastly, we're going to talk about some best practice applications on how to use fuel stabilizers. So let's get started by considering how and why fuel users should be concerned about the stability of their fuel. You know, the expectation by the user is that stored fuel is going to do what's expected whenever they need it to. But, you know, fuel stability issues that are unexpected will lead to greater uncertainty for different kinds of users, especially those who rely on fuels in an emergency. You know, emergency systems and what we call critical use systems or mission critical systems like hospitals, you know, they rely on stored fuel. And they can't have questions about will that fuel function properly when they need it to, because if it doesn't, you can have some pretty costly problems. Those problems can cost a lot, and this leads to budget uncertainty because the nature of fuel instability is such that most people don't know if it's going to happen to them, and so how can you budget? How can you account for the likelihood of something to happen? It's really difficult to do that, and so fuel stability contributes to budget uncertainty for these kind of groups. Now, failure to act on fuel stability problems, well, that can be a costly thing. How much it costs depends on who we're talking about. You know, it's going to cost the hospital a lot more than it's going to cost the fleet, which is going to cost a lot more than a farmer, but it's still going to be costly to all three of those. The kinds of costs, the kinds of things that can happen, you know, they can have shutdowns and disruptions. They can have the monetary costs that are associated with lost productivity if their equipment goes down because the fuel unexpectedly went bad in storage. There's also the mental costs associated with putting out the fires. You know, people have enough stress, professionals have enough stress in their lives not to have suddenly added problems, added fires cropping up that they have to expend time and resources to put out. There can be the cost of impaired emergency response scenarios. Basically, the inability to respond properly when a critical group is faced with a situation that they have to respond to. And based on past precedents, this is something to be very much worried about. You know, in Hurricane Sandy, Hurricane Katrina a number of years ago, the generators that they were relying on to provide emergency power, a large proportion of those suddenly did not work because the fuel had gone bad. So how much of a problem was that to those groups? other costs of inactivity, there's also, from a professional standpoint, there's impaired credibility. Nobody wants to be the one that gets blamed when a problem or when a failure happens on their watch. And that's exactly what can happen in a professional setting when somebody who's the head of a mission-critical organization and their fuel goes bad and they're not able to do something that they need to do. Well, that person looks bad. They may even be on the chopping line. So nobody wants to be put in that position. And so we at Bell Performance, we seek to ensure that these folks have the right answers to prevent those problems. So given all this, let's talk about the fuel itself. Let's talk about how and why the fuel goes bad so that we can understand a little more about the nuances that go into this issue. So when we talk about fuel stability, fuel stability is basically defined as the ability of a fuel to maintain its properties, to maintain its essential specifications over a given period of time as it sits in storage, or its resistance to decomposition over time. That's another way to put it. Now, fuel, unfortunately, in the real world, has a tendency to become unstable. And this is primarily because it gets exposed to environmental elements over any given period of time. So in order to understand how and why this happens, let's take a closer look at what fuel is made of. Let's take a closer look at the composition of the fuel. Well, fuel, of course, comes from crude oil. And crude oil gets split into its usable components at the refinery level through distillation columns. And so you get a lot of different things come off. You can get natural gas, you get gasoline, you get number 1 diesel, number 2 diesel, number 4, and then you get down to the number 6 heavy fuel oil, and then the stuff that's left over, which is the tar and the asphaltenes. Now, the stuff at the top of the column, the natural gas, the gasoline, the naphtha, number 1 diesel, those are called distillate fuels. And the stuff at the bottom, the heavier fuel oils, are called residual fuels. And a big difference between distillate and residual fuels is that distillate fuels have smaller molecules than residual fuels have. But all fuel, they're a complex mixture of different kinds of hydrocarbons. This is important to keep in mind because this is going to play into something we're going to talk about later, which is the fact that no two fuel samples are exactly the same. Fuel is refined from crude oil, which is a natural product. So the crude oil that comes out of the ground in different parts of the world is going to be different than crude oil that comes out of the ground from another part of the world. And the fuel composition, what it's made of, affects its stability or its ability to resist decomposition over time. Gasoline molecules are smaller than diesel molecules. Gasoline is typically made up of 4 carbon to 12 carbon chains, where we see C4 to C12. Diesel is made up of larger, heavier molecules, starting with 8 carbons and going up to 21 carbons. Now, at the refinery, you can see a simplified schematic here, but even though this is simplified, you can see there's still a lot of different parts that that play into making up a refinery and enabling it to do everything that it's supposed to do. Now, for every barrel of crude, barrel being 42 gallons, you typically get about 40% gasoline, about 20% diesel fuel, about another 10% jet fuel, then another 5% fuel oil, 4% LPG, that's natural gas, and then about 18 to 20% of other products. Now, when we start talking about molecular composition, this is important to consider. The reason why we're bringing up this refinery, the reason why we're bringing up the issue of how much of different kinds of fuel you get out of crude is going to be important because that's going to play into the question of how fuels have changed over time. So just keep those facts in mind. Now, the processes that compromise fuel stability. You know, the chemistry, when you're talking about why fuel goes unstable, the chemistry of it involves essentially the chemical conversion of precursor molecules into species of higher molecular weight that have limited solubility. So, what do we mean when we talk about that? Okay, well, first of all, we have to start with the fact that all fuel starts with the presence of certain unstable molecules, what we call molecular precursors, that are already existing in the fuel. Some fuels will have more of those, some fuels will have less. Now, these molecular precursors, they float around in the fuel, and they want, because they're unstable, inherently they want to react with other things to try and make themselves stable. Now, as the fuel gets exposed over the course of its life, as it gets exposed to what we call catalytic elements, certain kinds of things, these things help contribute to the start of chain reactions. And as you know, the nature of a chain reaction is such that once you have one reaction, that leads to 2, which leads to 4, which leads to 8, and so on and so forth. Now, the result of these chain reactions is that a lot of these molecules that previously were stable in the fuel get turned into unstable ones. And so what happens when this happens is that you have certain kinds of chemical reactions that happen. And these reactions, the two main kind are oxidation reactions and hydrolysis reactions. Now, without going into the chemistry of all of those, which isn't really something we need to do, basically, oxidation reactions are reactions that involve exposure to oxygen, and hydrolysis reactions are reactions that involve exposure to water. So, we know that fuel instability is a result of these chain reactions between the unstable precursors in the fuel and the stable molecules. We know that those reactions lead to fuel instability, and that these formerly stable molecules suddenly get altered and become unstable. But why does that matter? We say, so what? Well, why that matters is because these stable molecules that are reacting, they start linking up, they start reacting with other molecules, and they start forming longer and longer and longer polymers or chains of molecules. And eventually these molecules get so big that they're no longer able to stay soluble in the fuel, and they drop out. Now, just a minute ago we said that the fuel molecules get exposed to certain catalytic elements. And what we meant by that is that there are certain things that make it more likely that fuel is going to go unstable, so to speak. Exposure to these kinds of things is what speeds up or accelerates the decomposition of fuel. So what are these things? Well, the first one's water. Water contributes in a number of different ways. It contributes oxygen for both oxidation and hydrolysis reactions, and it also provides an essential medium for the growth of microbes in fuel, which is something we'll talk about on the next slide. So exposure to water helps speed up fuel instability. Also, of course, exposure to oxygen. That basically air. You know, if you take fuel and you leave it exposed to the air, apart from the fact that it's going to evaporate, the exposure to that oxygen is going to make that fuel go unstable faster than if you kept it sealed up and away from oxygen exposure. The third one, metallic catalysts. There are certain kinds of metals, including copper and brass, that if the fuel gets exposed to them, and if they get dissolved into that fuel, they will actually catalyze these reactions just by their simple presence and speed them up, make them go faster. Fourth one, heat. Heat is a catalytic element because it provides energy. All chemical reactions need a certain energy input at the beginning in order to make them go. And so, I mean, we've all seen it in practice in a lot of things in real life, that when the weather's warmer, there are certain things that tend to happen faster. It's because there's more heat in the ambient environment. So Warm fuel is going to be more reactive than cold fuel. And the same thing can be said for light. Light, if you leave fuel exposed to light over a period of time, that light is going to provide some energy that's going to make these reactions happen faster. And then the last thing we said just a minute ago, microbes. When you get microbial growth in fuel, these produce acids and they produce byproducts of their biological processes. And these combine together to destroy fuel quality. So 6 common things that exposure to one or more of these things, usually more, exposure to these things results in accelerated formation and expansion of unstable molecular precursors in the fuel, which cause chain reactions that lead to instability over time. But how do they lead to instability? What do these precursors do once they're present in the fuel? Well, like we've been saying, they cause chain reactions in the fuel that create longer and longer polymer molecules. Eventually, these molecules get so big that they can't stay in solution, they can't stay dissolved in the fuel any longer. So when this happens, they start to fall out, and you start seeing a darkening of the fuel. You start seeing a sludge formation as these molecules fall out of solution. So for fuel users that have this problem, what are they going to see from a practical standpoint? What is this going to do on a practical level? What are they going to see? Well, because undissolved molecules, heavy molecules, don't stay, because they don't stay dissolved in the fuel, and they're so big, they don't combust fully, they don't burn fully. And so because they don't burn fully, there's a couple of things that you'll see. First of all, you're going to get deposit formations. Even before they reach the combustion chamber, you're going to see that that sludge, those heavy molecules, are going to collect in areas like in injectors. Of course, in combustion chambers, you're going to get deposits that form there. You're going to get deposits in all sorts of areas in the engine. And anytime you get deposits where they're not supposed to be, that's going to affect the performance of that equipment. And that leads to loss of mileage, both because you have deposits, but also because, as we were saying, these newer heavy molecules, they don't burn fully, so that portion of the fuel is not giving the maximum amount of energy and maximum amount of work that it's supposed to give. You're also going to get raised emissions because they don't combust fully. You're going to get a higher incidence of black smoke. You're going to, if the diesel engine has a DPF system, a diesel particulate filter system, that's going to get filled up faster, which causes you to have to service it or regenerate it more often. So remember we said earlier that we were going to talk a little bit about how fuels of today compared to the fuels of the past. Because we've mentioned a number of serious effects that people need to be concerned about. And for people out there who have been around a long time, have been around long enough to have seen fuel from the 70s and the 80s and the 90s and so on and so forth, you may wonder why we have to be, why are we talking about this issue now? Well, the reason is because fuel is different now than it was in the past. There are some things that have happened that have changed in the fuel that have caused them to be different. The big one here is that fuel, the storage life, the usable life of fuel is shorter now than it used to be. If you go back a few decades, if you go back even to the 60s and the 50s, the U.S. Army did a study that showed that where they basically said that stored diesel fuel should have a reasonable shelf life of 5 years or more. That's way more than is the case today. So why are fuels less stable? Okay, this is where we're going to touch back on the whole reason we were talking about earlier when we talked about the kinds of things that you get out of crude oil. Remember, we saw the schematic of the refinery, and we talked about the percentage of gasoline and diesel and such that came out of fuel. Basically, what it comes down to is the demand for gasoline and diesel is greater than it ever has been. They're having trouble getting enough oil out of the ground to meet that demand. So the only solution to meet it is to try and get more gas and more diesel out of each barrel of crude, to get as much of it out as you can. Now, it used to be, before 1972, it used to be that you get about half distillate fuel. Remember, we talked about distillate versus residual. You would get about half gasoline and diesel, and then the other half would be the residual stuff that would mainly be used in industry. But they started employing catalytic cracking processes in the 70s, and now they're able to get like 93% gasoline and diesel out, and only 7% is the residual stuff. Now that's great at first, right? You're able to get more fuel. You're better able to meet the demand. But the problem is that basically, without going too much into the chemistry of it, the catalytically cracked fuel that they're able to make is inherently less stable because of the results of some of the chemistry processes at the refinery that they use. So it in and of itself is less stable. So virtually all the gasoline and diesel that you are going to be using has some amount of catalytic cracked stock in it. And so by its very definition, it is not anywhere near as stable as it used to be. The second big one is the ultra-low sulfur introduction in around 2006. They took all the sulfur out, which was great for the environment, but it created a diesel fuel that had virtually no resistance to microbes. And microbes are a key reason why fuel goes unstable faster. So the basic difference, the Army said in the 50s and 60s you should get 5 years out of stored diesel. Now you can have, you could have it be as little as less than a year if you get microbe problems in it. If you don't get microbe problems in it, you might be able to get 2 years. But you're not getting 5 years out of it without having problems. All right, how do you know if fuel's gone bad? We know that fuel doesn't last as long as it used to, but how do you know if it's gone bad or not? Well, there are a number of things you can do. The first things, which are really simple, is that you can do sensory tests. You can do a sight test, and you can do a smell test. Just take a sample of the fuel, look at it. Does it still look clean and bright, or is it darkening? That's a very simple way to tell. And you can smell it. Does it smell like, that clean solvent smell that diesel fuel or gasoline is supposed to have? Or does it have kind of a sulfurous smell? If it's got a sulfurous smell, then that's indicative of microbial activity. So these are pretty simple to do, but you would be surprised at the number of people who don't even think to do this simple thing. So sensory tests are good to use, but they're not the be-all and end-all, because a sensory test can only give you a generalized conclusion. Yeah, it looks good. Yeah, it looks bad. What you also need to do is you need to do quantitative testing. And by quantitative testing, what we mean is ASTM stability tests. These are the only reliable way to predict and assess the stability of a fuel sample. The key one that's spec'd in the diesel fuel specification is the D2272, the Accelerated Stability Test. It's the only one that is the legal definition of how stable a fuel is. And now there are other ones, like there's an overpressure test, there's one for thermal stability, but most diesel fuel users aren't really going to have to mess with those. Now quantitative testing is essential because it's the only thing that will tell you from a measurable level what condition the fuel is in right now, and it's the only way to really be able to predict with any kind of accuracy basically how much longer you have before that fuel is going to go bad. So at this point, we know how the fuel goes bad, and we know the causes, we know the processes that go into it, we know, and we can even see how to more definitively assess a fuel's condition. The question now is, what do you do about it? How can you protect fuel from becoming unstable in storage? Well, let's talk about that now. the bottom line answer, which is up on the screen here, is because you cannot completely prevent fuel from being exposed to the kind of things that make it go bad, or what they call environmental bad actors, because you can't keep them away from all of those, the only way to protect the fuel quality and to protect the stability and storage is to treat it with a stabilizer to prevent the reactions from happening in the first place. And in order to do that, you need a fuel stabilizer. Now, Bell Performance's fuel stabilizer is called Dee-Zol Life. It's typically used at a 1 to 2,000 treat rate. It's not the only fuel stabilizer out there on the market by any means. There's Stabil, there's any number of other ones. And the purpose of our presentation today, the purpose of this is not to say you need to go buy Dee-Zol Life stabilizer, because we know that there are other choices out there. So what we want to do is we want to give you some things that you can look for, or so that you can make a good decision about what you're going to choose. And so, when we say that, what we're talking about is diesel. There's no two kinds of diesel fuel that are exactly the same. We talked about the differences in composition. Diesel fuel from the North Sea is different from diesel fuel refined from oil from the North Sea is going to be a little bit different composition than diesel fuel refined from Saudi Arabian crude oil. And so that means that no two fuels are going to be exactly the same. And so in order to make a decision, and the reason I bring that up is because you don't know what kind you're getting, basically. That's what we're trying to say. You know that fuel is different even from station to station, so there's no way for you as a consumer to know exactly what you're getting. So you don't know, exactly what kind of stabilizer is going to produce the best results. You have no practical way of knowing that. So if you can't know that practically, well then, the best thing that you can do in making a decision is to make sure that whatever you choose has the best chance of being able to be most effective in the most different kinds or different compositions of diesel fuel. So how do you do that? Well, a stabilizer or a stability treatment that's going to be effective is going to have to address at least one of the major chemical pathways or major chemical problems that arise when fuel's going unstable. Ideally, it will address all of them. So what that leads us to is that there are essentially 5 important components, 5 types of things that need to be present in an effective stabilization package. And so when you're looking for a fuel stabilizer, your best choice is going to be one that has all 5 of these. What are they? First one is antioxidant. Antioxidant is the thing that addresses the exposure to air and the reaction of oxygen in the fuel. It needs to have a stabilizer. Now, by stabilizer, we've been calling this stabilizers, but really what we mean is that something that neutralizes acid-base reactions in the fuel. Third thing it needs to have is a metal deactivator. Remember we said there are catalytic metals that speed up reactions. A good stability package will have a metal deactivator that neutralizes these. It will also have a dispersant. A dispersant is going to take the heavy molecules that have started to drop out of solution. It's going to keep them away from each other. It's going to keep them from reacting, which means they don't get bigger, which means it stretches out the effective storage time of the fuel. And then lastly, you're going to want something that has a corrosion inhibitor in it that attaches the metal surfaces and prevents attack from corrosive agents like acids and water as well. The best stability treatment will contain all 5 of these. Obviously, we formulated Dee-Zol Life to contain all 5 of them because we wanted it to be the most effective stabilizing treatment that it could be. Now, a quick word about multifunction stabilizers. There are a lot. Stability is one of those things that when somebody's formulating or bringing a multifunction additive out in the marketplace, they will always claim that it has stabilizer in it. Now, the thing that you need to watch out for here is that if you have something that claims to do a bunch of different things, you need to know, if it's got a really, really low treat rate, then is it going to have a high enough treat rate to actually deliver enough active ingredients to do everything that it claims to do? A lot of these simply lack the formula space. They claim that you only have to use a tiny little bit, like 1 ounce to 30 gallons or 1 ounce to 80 gallons. That's one of them out there that claims that. And when you start talking about that stability and stabilization as one of its claims, well, there's no way that it can possibly deliver enough of that kind of active ingredient in order to be a really effective product. So there's a lot of those out there, and unfortunately it makes the whole industry look bad. So Dee-Zol Life used at a 1 to 2,000 treat rate, which means there's 500 parts per million of it going into the fuel, which is plenty enough to deliver enough actives for all 5 of those types of components. Now, some of the fair questions that get asked about Dee-Zol Life and about stabilizers in general. The first question that we would expect someone to ask when we're talking about this whole issue is, well, if I use it, how much more, what benefit am I going to get? And what they mean is, how much can it extend my fuel's life? The first thing that you have to realize is, like we said, there's no one-size-fits-all answer because all fuel compositions are a little bit different. If you wanted to know for sure, you would take a fuel sample and you would treat it with Dee-Zol Life, and you would do an ASTM stability test on it. But most people aren't going to do that, and they shouldn't have to. So the stock answer that we give is that for most fuels, Dee-Zol Life will extend the storage fuel life by at least twice. So if you were expecting to get 1.5 years out of it, then all other things being equal, you should be able to get 3 years if you extend it or if you treat it with Dee-Zol Life. Another fair question that gets asked a lot is, if the fuel's already gone dark and unstable, will a fuel stabilizer reverse that? And unfortunately, the answer to that is no. Once the fuel has gone bad, once those molecules have dropped out, there is nothing that's going to break them back apart and put them back into solution. That's why the important thing about applying a stabilizer is that you have to put it in the fuel at the beginning when it's fresh, before those chemical reactions have happened. Now, there are some options for using bad fuel. There's cetane. You can do cetane improvers. You can use a combustion catalyst, but how effective those are going to be depends on how bad that fuel is. And a lot of the times, if it's really bad, there's going to be no way to use it short of maybe doing some fuel polishing to get some of those asphaltenes out, or even just having to dispose of it, which is what you really want to prevent in the first place. So how to apply a fuel stabilizer like Dee-Zol Life? As with a lot of other things, including like biocides, the effectiveness of a stabilizer depends on getting it well mixed into the fuel and applying it at the beginning. There are there's 4 main ways that people apply these kind of products. Probably the best way is to apply it, to add it to a storage tank, and then circulate the fuel for a given amount of time. You can also do direct injection. Now, a lot of people don't have this ability, but if it's someone who does bulk fuel storage, then many times they will inject the stabilizer into the fuel stream as they're adding additional fuel. That's another good way to get it mixed in. Who are the kinds of people, the kinds of markets that have the most need for this kind of thing? Well, municipalities and fleets, anyone who relies on preserving the quality of stored fuel, they're going to need to consider fuel stabilizer treatments, because if they don't, they're going to see drops in mileage, performance. They're going to see, they can see excessive emissions, especially in standalone systems, like when they fire up generators to do load banking, and you get that big puff of black smoke. They're going to see deposits forming in the engine, which are going to adversely affect the performance of that engine, the performance of that equipment, and they're going to get sludge buildup in storage tanks, which can lead to things like plugged filters and lost heating value of that fuel. And of course, if it gets too bad, they may even lose dollar value. If they have to dispose of fuel that's gone really bad, well, then they've lost the amount of money that they've invested in that. Mission-critical installations and generators have a tremendous need for fuel stabilizers because they're mission-critical by nature. It's critical that their stored fuel does what it's supposed to. If it doesn't, their systems are going to be difficult to start, and there's a possibility that a critical system may not even function properly when it's needed, and that would be an absolute disaster. What would be the potential cost if something like that happened? How much did it cost that hospital in New England during Superstorm Sandy a few years ago, which had its generators failed in the middle of the storm? How much did it cost them, both in money and also in public relations nightmare? That's a fair question. So, in review, Dee-Zol Life is Bell Performance's fuel stabilization treatment used at a 1 to 2,000 treat ratio. It contains what we think is the industry's best combination package of all the 5 kinds of active ingredients that you need to have an effective stabilization package. If you have any questions about Dee-Zol Life, about fuel stability in general, you can email them to me at the company. Our emails are first initial, last name format, so you can see on the screen. My email is ebjornstad@bellperformance.net. So we hope you found this useful, that you got some useful takeaways out of this. Again, my name is Eric Bjornstad. I'm Technical Information Director with Bell Performance. And this has been our discussion of fuel stability treatments and Dee-Zol Life from Bell Performance. Thanks for joining me today, and hopefully we'll see you next time. Bye-bye.